All right, so class has started. So what we are going to be doing today is pivoting to drawing this in a schematic view because I didn't have a chance really to figure out what was wrong with the layout view and why it was behaving poorly or oddly. I don't know if it's behaving poorly or not. I went ahead and drew this circuit in, well, so this is the exact, just the startup circuit and the beta multiplier reference circuit, and I'm just going to give you guys a simulation to show that it's behaving as we would expect it to. Actually, I wrote this on a different computer, so I need to update where my C5 models file is located here. I'm also going to show you guys something that I found incredibly useful while putting electric on my desktop computer in my office yesterday. So I think that's where it's located. 90% sure that's where it's located on this particular computer. So write my spice deck. Thank you. Add trace. I'm looking for the current through MB1, which is the transistor 1 of my beta multiplier. And you can't really see it, but if I change this scale from 0 to 5 microamp steps, and 50 microamps here, effectively spot on 20. This was achieved by using a 20 kilo ohm resistor, and I just made all of the transistors, discrete transistors. So 10 by 100, 10 by 2, a 20 by 2 instead of two 10 by 2s in parallel, etc. So this is the one that I called ideal because it's got everything lumped together. And then I made this one. This one actually, everything to the left of this vertical line that I'm making right here is the beta multiplier circuit with the reference circuit. Everything to the right is generating all of the bias voltages and all that kind of stuff for later stages. If we simulate this guy, let me close out this LT spice.
For that 20 kilo ohm biasing resistor value, were you able to calculate that using the equation?
I played around with stuff.
Okay.
Yeah. So that gave me the 26.5 that you gave me was a place to start. Okay. And then I just went from there. The reason why it's not going to be exact is because of channeling modulation effects that are ignored when deriving that equation. So that's a good baseline thing. And I'm going to talk about that here. Oh, I have to update this spice command as well. Sorry about that. I no longer actually use that vout thing, so I can delete that. This one takes a little bit longer because there's so many more transistors. But if we look for ID for MB1, put this on the same scale. Pretty much spot on at 20 as well. Had to use a different size of resistor to take into account the fact that everything was in parallel, but it's working effectively as intended. And so what I'm going to show you now is a couple of other critical currents that are generated. So let me go back to electric, okay? So we just found the current that's flowing through this particular NMOS transistor. Hopefully everybody who's on Zoom is paying enough attention so they can see what I'm doing. So we found the current through this guy right here. This guy right here is supposed to just be a copy of it because this serves as the reference current for the wide swing current mirror, the large or the long transistor of the wide swing current mirror. This guy right here is another important one because it serves as the reference current for the cascode portion of the wide swing current mirror. And then we have these transistors over here So this guy and this guy together in a cascode are the reference current for the NMOS based wide swing current mirror that's located down here. So we're just going to look at what I have labeled as MNF ref1, ref2, and then P ref1 and P ref2, and just see how things are doing. So if we add traces, ID, M, MN ref1, and I'm gonna copy that so that I can just do it again in a moment. So we see it's around 25.3. Ref2, 26.9-ish, okay? So a little different than what we're expecting, a little larger. The reason being there, if we look at effectively our signal path between this point and VDD, we only have a single equivalent transistance, okay? So this guy right here isn't eating up a large amount of headroom, and so we are seeing a larger current able to flow through it. This guy over here has two transistors in parallel, or excuse me, two transistors in series, but the drain of this one is tied to the gate of this one through that long feedback loop, effectively making that as small of a voltage drop as is literally possible there. And so we see that we have a larger amount of current flowing through it as well, okay? If we look at MP ref 1 and 2, so let's change this to P. A little over 28. And I'm going to look at MP ref 2. Because these are in cascode configuration, they have a lot more, they match much more closely to each other, okay? So effectively, we're not getting perfect copies because channel length modulation is a thing. It's close enough for what we are doing. So these are all of our reference currents. They're all in roughly the same ballpark. So I'm going to call that a win. What I'm going to do now is delete all these and show you guys something else. The different voltages that we are generating to use to bias things later on. So we're going to have V bias 1. So let's talk about this guy just really quickly, okay? So we measured that our threshold voltage for our PMOS transistors was somewhere in the ballpark of 0.9 volts. For a VD sat of around 250 millivolts, which is reasonable for this size of transistor, we would expect this voltage to be at about 3.8 volts. It's at 3.73, so that's pretty good. When we look at V bias 2, it's a little bit lower, which makes sense. It's supposed to be. If we look at it over here, V bias 2 is the gate voltage for all these other transistors down here. So we're in the ballpark of 1 VTH lower. Okay, so that seems reasonable. Now we're going to look at V high while we're at it, and then we'll see why it's named V high. So V high is at about 4.6 volts. So the way that this is drawn in our diagram might imply that V high should be at a lower potential than V bias 1. The reason that it isn't is because V bias 1 is tied to this node down here, right? So we're forcing it to be at this lower potential by this feedback configuration, connecting the drain of what I have MP wide swing 3 to the gate of MP wide swing 1. That is very intentional. So our high voltage, which I don't think we're actually going to wind up using for anything. We're going to use V bias 1, V bias 2, NCAS, PCAS, bias 3, and bias 4. But high should be the highest point that isn't VDD. And as we'll see in a little bit, low will be the lowest point that isn't ground. So let's keep on adding voltages. So let's look at V bias 3, around 1.7, V bias 4, around 1. So a threshold voltage plus a VD sat is about where it's supposed to be. It's a little bit higher than I would like. Preference, it would be about 0.95 volts or exactly at 1. Is a little higher, but we're not eating up a lot of headroom here. It's, to me, not worth the effort of going through and playing with the sizes to make that work. And finally, if we look at V low, a little bit under a threshold voltage. VPCAS and VNCAS for our floating current sources that we're going to have if we get to do the push-pull output stage are going to be right there in the middle because that's where they're supposed to be. So effectively, we have generated a multitude of different voltages that we can use to do things. V bias 1 and V bias 2 are going to be used to bias cascode current references, PMOS cascode current references. V bias 2 and V bias 1 are going to be used to bias NMOS cascode references. So once we get to this point, then we get to choose what type of differential amplifier we want to use. So let me explain what I mean here. Let me draw a shitty picture. Edit. That's why this isn't doing what I want, because I'm on the wrong thing. So for our differential amplifier, how we learned it in 336 and all that kind of jazz was going to be something like this. So here is M3. Actually, I should move that to the other side so we can see where the input's going to be applied. Sorry about that. So this is effectively our non-inverting input terminal. Here's our inverting input terminal. Here's our output terminal that's going to go to a different stage. And then here is our tail current source, ISS. The way that we have developed our bias circuit allows us to have either this differential op amp or this one. like so, where let's see, let's call this M1, M2, M3, and M4. We effectively have the option of creating this current source with a cascode PMOS device, or we can create this current source with a cascode NMOS device. So the reference or the bias circuit that we've generated gives us literally the most flexibility we could possibly want, because we can do things on either side that make sense. So after this point, let's just say, for the sake of argument, that we went with this guy right here. We're going to chain this output into an additional gain stage. Well, chances are, so what do you guys remember about the DC biasing point of a differential amplifier? Not a whole hell of a lot. That's okay. So it's based on like hyperbolic tangent relationships for MOSFETs, which is wildly annoying, and the derivation bores you guys to tears for the most part. Perfectly reasonable. It bores me to tears as well. But effectively, what happened was you had a, so if we were looking at this on a plot, the output voltage had some high-ish DC value for the NMOS case, and then superimposed on top of that DC operating point was our AC signal. Well, that DC operating point is going to be a bias voltage for our next gain stage. So effectively, if we go with this route, then our gain stage needs to be a PMOS, common source amplifier. If we go with this stage, our gain stage needs to be an NMOS, common source amplifier, so that we're bringing the DC level of the output closer to the middle in each case before we get to our output stage. That's going to allow us the highest amount of variability from the plus side to the minus side. If we went NMOS into NMOS, we're going to have a very, very small amount of headroom to use. So we have to make sure that we're going NMOS into PMOS or PMOS into NMOS before we hit our output stage. So anyway, that's enough ranting about where we're going. Do this. Happy to answer and entertain any questions you may have, but I've already built it, and the schematic representation of doing it is much less of a pain in the butt than the layout version. I'm going to work on the layout version. I intend to work on the layout version this weekend. I say that because my first priority is making sure that all of your senior design reports are actually graded and returned to you, so that you have feedback and can update it before the end of the day. So that's priority one. Priority two, knocking out all the advising stuff, which I think Hayden, you're the only person in this room who has not yet advised with me.
Yeah.
We can take care of it immediately after this class if you want to. You can shoot me an email just letting me know what classes you want, whatever floats your boat. I'd like to get you released by this weekend. I don't think unless you have veteran status or honor status, you won't be able to register for classes until Tuesday. But just in case, I want to make sure that you're okay to go on Monday.
Yeah, we just do it right.
Okay, sounds good to me.
Is there?
So, fantastic question, Sam. I'm not sure if there's a hotkey for rotating, but one thing that I did to make my life easier. Edit. Oh, no. I'm looking for. So 90 degrees counterclockwise rotation is Control J, which the only thing that I've rotated in any of these would be a resistor. I did mirroring for everything. I don't know if that particularly matters because the source and the drain should be interchangeable. So it should not matter in the operation of the device.
Yeah, because I do see like the number
Swap. Yeah. But what I was going to show you guys is if you go to tools, actually I lied. If you go to preferences, and then you go to key bindings, and then you go to some operation that you want to do. So for instance, let's say edit, and we want to mirror, and we want to do a left-right mirror, which is what I did on all of these. We can literally add a keybind for that. So if I put my keyboard here, I could do Shift M will now mirror left and right. Press add. The thing that I did this for the other day, I went to, let's see, key bindings. Let me scroll up here so I can find it. Tools, simulation. And I made a keybind for set spice model because I got annoyed having to go through that stupid 3 windows every time for like 45 transistors. So I made a key binding for this. Since it's setting the spice model, Shift S or something like that. So setting the key binds up here is pretty straightforward. And if it conflicts with anything else, it will literally tell you in this drop-down menu here what it conflicts with so that you can't accidentally screw something up. So that should assist with the speed at which you're able to recreate this behemoth that I have drawn. And this is literally nothing different than the handout that you have. So, like I said, just let me know if and when you need input from me.
So it's kind of hard to make out, but it looks like both the SU2 and SU1, those are 10x2s.
Let me, oh, of course I can't use the touchscreen to zoom in. So MSU 2 is a 10x10.
Okay, I apparently do not have one about.
So I'll just put, well, I'll attempt to put just the beta multiplier part in here, as that would be what my preference for you guys to try to get done today is, because that would catch us up. Regarding the handout, you can borrow mine if you want to.
Or on the middle, so that way I'm not having that.
Yeah.
Oh,
I largely made these using a lot of copies of transistors, which is if you have a transistor selected, press Control M, and it will make a second instance of the same transistor. So that if you do it that way, it will have the same size, it will have the same spice model set, and you just need to change the label. I'm going to pop up to my office to get one of your senior design reports, and I'm just going to sit here and grade it until you tell me to do something else.
You just change the name of the transistor.
Those are,
No, that's not.
yeah, because the PMOS and MOS stuff has spice,
Yeah, but I mean, like,
spice model, but then you use miscellaneous annotation text.
I just don't, is that gonna copy over?
No, because it's not attachment to the transistor, it's just annotation next to it. So you need to copy that image. So how's y'all seeing your design stuff going?
It's actually, don't like doing anything. I'm just trying not to think about stuff I'm supposed to do. Don't catch up to you when it catches up. Uh-huh. See, that's how we get things. Yeah.
Well, I'm glad I got that over with. Yeah, Dr. Harmon's comments about not needing the FE necessarily surprised me. I was very much under the impression that we needed it for just about anything.
You can still call yourself engineer.
See, I wasn't even, I didn't think I could call myself an engineer unless I had that.
So
That's honestly where I was.
there's weird legalities in that, but you know, states largely don't matter.
Yeah, legally speaking, you cannot legally sell engineering services or offer yourself up as an engineer unless you have a PE.
Yeah, not directly.
There's some legal issues there, but
Which is why hunting for a job as an engineer is very difficult because everything that anybody wants to call engineering pops up. Be a culinary engineer, yeah, you're making sandwiches.
culinary, oh my gosh.
I'm not even joking, like that's.
No,
I
I know you're
guarantee
not,
it's a
and that
thing.
really is depressing. It's like,
Well, it's just frustrating.
all the work I've done to get my degree and call yourself a culinary engineer. Hey, brother, you're talking about, it was a surprise to me, your comment that you really don't need it for a lot of stuff, because I was under the impression you absolutely have to have it.
No. If you absolutely had to have it, more professors in our department, other than Dr. Cox, who is retired, would have it. I have been quote unquote working on it for years, which is true, but I have not actually taken the test because I have never sat down to study for it.
Well, I was talking more generally about the FE, not.
Oh, yeah, no, we highly encourage you guys to take it. Not because we're interested in making NCES a lot of money or anything like that. But the pass rate of our students is significantly higher than the national average, and that is something that we can point to as a recruitment and retention tool and all that kind of stuff regarding the efficacy of our program. It's also incredibly important that if you ever even think about getting your PE license, you take your FE as soon as you possibly can, because the longer you wait and the longer you get out of the habit of studying and doing any of that stuff, the harder the FE becomes. So I would encourage anybody to take it if they're considering any type of job. that might need a PE to take the FE during their senior year. But is it
I didn't
needed?
know,
No.
the MA department requires them to take it before they can graduate.
I heard that too about the civil.
Yeah. They don't have to pass it.
Well, to me, if you're gonna take it and you don't pass the first one, that kind of psychs you out negatively for the next time.
The faculty has to make that decision, that level of decision, if it's a graduation requirement. I would actually be for something like that. When I was here, we didn't have to take it, but Dr. Cox encouraged it so strongly, most of us thought that it was required of us.
Which,
So that's what I thought. I was in conversations with you and Dr. Vitari telling you, oh yeah, I'm taking it at this date, I'm already registered. I seriously thought that was a requirement for me to graduate.
Technically, no, but if you passed it, that's a great thing.
And I don't have to take it.
that resistor was on the high-risk policy resistor.
Yes, but for this, it actually shouldn't really matter, and you can't see it, but I used an 11.5K resistor there because that's what got the current that I was looking for. That was just, again, trial and error kind of thing based on starting a 26.5K and just making it work. Are you facing any difficulties? Need any assistance? Or you guys good to go?
Just follow through it. So the resistor I have isn't quite the same as yours. My text is horizontal. Is there a different model resistor, or is that just the way yours was worked out?
Just rotate the text.
Normal.
You can rotate the text.
Yeah.
So I used a high-res poly 2 resistor, and I think it automatically does it. That shouldn't matter. Also, it's 11.5K.
Okay, I couldn't quite make.
Yeah.
Okay.
No, so it looks like the text is still horizontal there, but you can rotate the text by clicking the. Rotate on there. But if not, if you just have the text selected and press Control J, to rotate it.
I do have a question.
Yes.
Of something on my model that is not present on that one.
Okay.
When connecting beta 2
Mhm.
to A, I get a connection like a dot for that gate. And also this gate. But up there, it doesn't have that.
So that's just
I don't think it-
where I chose stuff. So let me click something here. There isn't.
Is that?
So all of your gates are tied together. And then you have that feedback thing. These sources are tied together to these drains. So if we press F5 right now, oh, sorry. It's finding 13 errors, and I bet the overwhelming majority of those errors are extra pins.
Okay.
That you'll go through and delete them, and I bet it'll look more like mine. That shouldn't actually mess with the behavior of anything, it's just, it doesn't like nitpicky things, like I guarantee you that that little stub of wire is an error,
Oh, probably.
because it's a dangling wire.
I'll get to it.
Yeah.
How did you show where all those pins were?
So if you press F5.
Yeah.
And then you press the greater, hit enter to clear that, and then press the greater than key or the less than key.
That one's never really done.
That's literally what I just did.
I know, I saw
Let me try it again.
that.
No worries.
Maybe I pressed shift for that because so it's not a period.
Yeah, I
Anyway,
guess so.
yeah.
Okay, I just assumed it was like just the key, but.
Yeah,
okay,
so
whatever.
that, and then F5 again. And then one down there. Better. Yeah, you're just gonna be deleting things that you literally can't see because electric is incredibly finicky. Aiden, how are you doing?
Good, just about everything that you, that's visible on there.
Okay,
I'm not sure if I'm here, I'm a little bit like.
so your drain of MSU 3 should be connected to the gate of MV 3A and MV.
Oh, right. Yeah.
All right, I'm running DRC and it's showing me I have all these unnecessary pins.
Yep, just delete them.
Okay. I was trying to delete them and okay, yeah, I see.
Yeah, that's the exact same issue that Sam was having. Ultimately, they shouldn't really matter too much, but yeah, so just hit F5 and hit OK, and then look for the next one, and it will highlight it for you. And then F5 again, and just keep on doing that till you get 0 errors.
You know, up here
Like
on.
wax.
Pretty
I
much.
need to export this to BD.
So that's, can just click one of the pins up top and Control E for export.
You have to call it, it knows ground's ground.
Knows what?
It knows the ground is ground.
Yeah, you don't have to do that one.
I think they do a better job of preventing me from making all these unnecessary pins.
It's the order at which you place the elements and then make the connections. So if you put down a transistor and then you make yourself a little stub of wire and then you put down ground and then connect that little stub of wire to ground, you've created an unnecessary pin because you didn't wire that
terminal of the transistor directly to ground using a single piece of wire. It's, yeah. So 0 errors?
Yep.
All right, run your simulation, see what happens.
All right, don't have spice code written for just.
So let me see what's going on in the chat there, but start with VDD 0 DC 5. Gavin, that's correct. The value on the resistor is 11.5 kilo ohms. Sorry if I've left you hanging here. I don't know how long ago you typed that.
You want to pull that text out? Away from the resistor.
Now it's not as pretty. Yeah, and so I just did a transient for 5 milliseconds or something like that. It really doesn't matter. You could technically do a DC operating point as well.
I'm probably butchering the
Dot tran
doctrine.
and then 5M.
Just 5M.
Yeah, and yeah, no space.
0 V5, no, V0 DC 5.
Yes. All right, so it didn't give you errors there, so that's good. If you labeled things, just type ID, open parentheses, B1.
The case sensitive. MN or MN?
And for me, it's MM. Because it's going to be M and then the label that you gave this transistor. I labeled it as MB1.
I did as well.
Go. So did you label it with spice text?
No, this is,
Or annotation, I mean.
that's an annotation.
Okay, so that's why it's not doing it. So you're going to be so annoyed.
Yeah.
Click on that. Press Control I,
So
label it there. So no, not annotation. You're literally giving that transistor that name.
okay, I missed.
Sorry, I didn't clarify that.
That's
Yeah.
gonna take a minute.
Yep. But just do that one for now and we'll see if it works correctly.
I'll come back.
What's the transient command?
Dot tran.
Tran, wow.
However long you want it to run as a DC circuit. So
That's all I need on that line.
yeah, dot tran and then some time duration.
I know it's going to be plenty of time.
Sure.
Okay.
It's DC. And then dot include C open parentheses and then, or dot include and then the file path to C5.
Is it parentheses?
No,
it doesn't.
Oh,
no, I
Dot
thought
include
you said,
C
yeah, I'm sorry, I thought that you said,
20 microamps. Right, okay. So
I just need to go label the rest.
yeah, so go label the rest and then you can start working on the rest of the circuit.
Oh,
But the beta multiplier part with the startup circuit is correct. So that's great. Progress has been made today. Stuff is working the way that we intended to. That's always good.
Yep. So.
no, that's fine for, actually. What did you say?
I was asking what they were talking about, like the mention annotation text, and I'm using annotation text.
Okay, so let me show you. So I did things slightly differently here than we did on the other things. Just so that I could
That
find
mouse isn't working for some reason.
So click on any of your transistors. Press Control, with that one selected, press Control I. Give it a name there.
Okay.
And that way, that name is what it has inside LT Spice as well.
So you also did annotation text that.
I didn't do any annotation text at all technically. So sorry for not clarifying that.
Okay, so it annotates with the name that you give it.
Yes. Okay. So if you give it a name that isn't The default name, okay, so just to make sure I'm not making the same mistake. So let me explain what we are talking about in the class, and I'm sorry that I didn't mention this easier. With a particular transistor selected, press Control I, and you'll notice up here in the name field that I gave it a name of MB3A. That is so that when I'm trying to find it in LT Spice, I know exactly which one I'm looking for, because if I don't, they're just given default names of MNMOS 0, MNMOS 1, etc. And you can't actually see that on the drawing, okay? Now, for this Spice model stuff, with the transistor selected, if I go to Tools and Set Spice Model, I am able to do that. I made this keybind here, Shift S, to allow me to do it more quickly. So if I put a PMOS transistor down here, with it selected, if I hit Shift S, it brings up the Spice model. I would call that PMOS. And then I drag that text down here. And then with the transistor selected, I give it a name, PMOS 5, and give it the correct dimensions. And now that information is on there, and I move this up over here. And now I've told LT Spice that when it sees this, it's a PMOS, and when I'm looking for it to find the current or something like that, it's already has a specific label that's on the picture so that I don't have to go hunt through things. Did that clarify things, Gavin? All right, sorry for not mentioning that I wasn't using annotation text earlier. I completely forgot about it. I just knew I was going to have so many transistors that I was going to get confused. So I named them when I put them on the field.
Well, I'm glad we made the progress to the point where we could actually solve those problems.
Yeah. You got everything labeled, do you think?
Sure
All right, so now, sorry, if you want to borrow that, start working on all this other jazz.
Yep.
So how I personally did it is I just divided it into little blocks. So I'd make that strip, make all those connections, and then after I had made how they were connected to each other, I connected it over here. And then I made this strip of transistors. After I got all their connections correct to each other, then I connected it, and so forth and so forth and so forth.
Mhm.
It's really easy to make one small connection and then half your circuit has drain currents of 0 because one pin is in the wrong place. I say that because that happened to me yesterday.
The diagonal preposition when you end a sentence with two,
Think so.
is that the right English nerd phrase?
I don't know.
When you end a sentence with the word to, T-O, or is it dangling participle?
I know you're not supposed to do it. I don't know what it's called.
No, you're also not supposed to
That
start.
being- that being
a
said,
sentence.
that being said, you're probably looking at something I wrote, so.
Not you.
Yeah. I think the rule that preposition has to have something after it.
Yeah, so there's a way, but probably when you do it wrong.
I never liked
The
English.
word for when you do it wrong is incorrect.
I never liked English classes because they never could tell me why you weren't supposed to do something that way, other than you weren't supposed to do it that way. And did not have good. Did not have good practice.
Yeah, that's just the weird way English does it. My favorite feature of English though is that we just pick up words. There's a cool word in another language. We don't come up with our own.
No, it's ours.
Just, it's ours.
I mean, like, you know, that's fair. Like, I'm glad of the French that we do have and not the French that the French use, because that language doesn't make a lot of sense. But their words sound cool.
The French language is very, very rigid and not adaptable.
Yeah.
And that's becoming a big problem as technology advances more quickly than their language will be allowed to adapt. Yeah.
One of the things I laugh about is their word for pool. The French word for pool is pissin.
What's?
Pissin. That's the word for pool in French.
Okay. Yeah. I don't know.
We don't like having the French come to our pools in the United States.
That's good. Okay. My dad had to take a work trip to France, and yeah, he ran into that. They don't have a lot of words that translate properly. So when you're doing technical work, you end up getting about like 25% of what you normally would through a translator. So it's horrible.
Oh, I just had a really bad thought. Is that why they haven't won World War? They couldn't come up with proper munitions or weapons because they couldn't come up. Yeah. Just. I took it out to look at it and then just did not put it back.
We're not doing the 30 by 10, we're doing the.
I think it's 3.
Oh,
Yes.
Yeah.
Oh, no, it's 2, because we are not doing 30 anything. We're doing 20s for the people.
That's right, yeah.
Okay.
Those are
So I get one more.
a pair of 10 by,
10s. Because those are the long length transistors for the wide swing current.
oh, yeah.
So transistor 5 for the wide swing current mirror has to have a length that is at least 4 times as long as the other transistors in the
That's right.
cascode configuration. And we are making it 5 times as long because
Can't hurt.
exactly right.
Okay, that's right. So this you're calling P. W.
All right, spent 10 minutes and I've created 1 page.
Yeah, it's all distracting with it there too.
Please don't sit there. Thank you.
any of you guys remember, this is another English nerd nitpicky thing. Like when you're making a list and it all has the same form. So like this says batteries dying too frequently and then moisture trapping and spoiling the feed. And it should be like battery dying too frequently, moisture becoming trapped. Like all of the verbs should end in the same.
Yeah, you want consistency. Really, rule of thumb is, does it sound correct?
Yeah.
If it sounds good,
There's-
probably.
I think they all need to be, if that's like present tense, ongoing, it's happening.
Right, so
I
maybe
think they
that,
all need to be, or they need to explicitly like,
no, I'm trying to remember what it's called. I know what I'm bitching about. I don't remember how to explain it correctly from an English nerd perspective. I'll figure it out.
something about this.
That's not subject verb agreement. It's,
No, that would be,
There's not quite repetition or redundancy.
So on all the unlabeled transistors, those are all 10x2s.
If they are unlabeled NMOSs, then they are 10x2. If they are unlabeled PMOSs, they are 20x2.
Okay.
Oh, class ended 6 minutes ago. Quietly working away. So we are getting closer and closer to the end of the quarter, and I would like for us to continue making progress on this. So I am going to, I think, dedicate Monday's class to finishing the remainder of this up, that time to allow you guys to finish the remainder of this up. Then we are going to move along to the differential amplifier stage, which should go relatively quickly because it's only 6-ish transistors. So we might have a review-ish thing about the operation of the single stage op amp, which is what we're going to be using as our differential stage, because we want differential input, single-ended output. So why beat around the bush and just go for it since we're running low on time. So we'll review very basically the large signal and small signal operation, just so we know what our expected operating points and stuff like that'll be. We should have some idea of what our gain is, and then we'll use our circuit to actually measure our gain for small signals and all that kind of stuff. I imagine that'll take 2 to 3 days-ish tops. Then we'll throw on a gain stage, talk about frequency compensation, and then work on the push-pull output stage and kind of call it a day. Because the schematic version of this is a lot easier to deal with, we might limit things to that just so that we can finish what I want to finish before the class is over. Because your exam 3 is about the Bader multiplier thing, I either need to revise that to be just do a schematic version, or I need to find time to work on it and kind of push something out to you guys to be like, if you do it like this, it works. Here it is. So I'll consider that over the weekend. But I think based on how much time we have left, and if we want to actually complete this damn thing, we've got to do something to expedite the pace. And this is the easiest way to do that. You've learned about what the layers are, all that kind of stuff. You've learned some techniques about minimizing size and all that kind of jazz. It's just finding the time to apply it. And if we're doing it just in this class, there isn't enough time to apply it before the quarter ends. So, all right, that's enough ranting out of me for today. So Hayden, I'll see you in 3 minutes to come do your advising. Grace, you're already done. Sam, you're already done. You're no longer an undergrad, so I don't have to deal with you.